before we can move into forces on an incline, we need to review just a couple things and review the true definition of a couple things. The first thing that we need to review is the normal forces. Okay, you don't have to write this part down necessarily, but I want you to think about what the normal force really is. It's the force of our surface pushing up on our object, or it's the force that our surface exerts on our object. And so far, we've dealt with things that are on a flat surface, right? Which has made our normal force go where? Up, right? It goes straight up into the air so far, because everything we've dealt with is on a flat surface. So if it's the surface exerting a force upward, so far our normal force has gone up all the time. But we need to shift our thinking a little bit to understand that if our force is on an incline, our normal force doesn't necessarily go straight into the air, right? Our normal force, we need to think of it now as perpendicular to the surface, okay? So if we draw our incline to look something like this, right? If we've got an object on an incline, right, here's my object. My force would look something like this. My normal force would look like that, right? Okay, it's pointed perpendicular to our surface, right? Wherever my surface is, perpendicular to that. Okay? Now we need to think about gravity. Where does gravity point? Like this or like this? Right? Gravity always points straight down. Always. No matter what. Always points straight down. So do we see a problem here? Yeah, we've got something at an angle. Right, that's a problem. So
angles, am I right, Jack?
we can't work with forces at an angle. So let's say we push the box down the incline, right? We've got an applied force. Let's say we've got friction. Do we see how now we've got, if I look at a coordinate system based on this, we've got lots of problems, right? Here's my coordinate system. Oops, that's not a straight line. Either is that. Okay, I'm trying to draw a straight line here. But if I look at my coordinate system, look how many forces are at angles, right? Assuming my gravitational force is straight down, right? But see how many forces are at angles? We've got problems, okay? So the way we fix that is that we're going to rotate our axes. We're just going to rotate our coordinate system to match the incline, okay? Yeah, it's much simpler. That way we don't have to work with 3 forces that have components. Now, what's the one force that has components? Gravity, right? So let's say what it would look like again. We shift our axes in our coordinate system to look like this. Okay, so all I've done is I've turned my coordinate system to match my incline. Okay, meaning if I were looking at it, this would be north, east, south, and west, right? All I did was shift that. So these are still the positive directions. These are still the negative directions, right? Because if you place something on an incline, what's the direction it's most likely going to go? Down. It's most likely going to go down the incline, which is why we choose down the incline to be the positive direction, right? Because most likely when you put an object there, it's going to come down the incline. So that's why we choose it to be the positive direction. If I draw my forces on my incline or on my object, right? Now I have gravity, which goes here. Normal force, some applied force maybe, and some friction maybe, right? So you see the only force that has components that we have to deal with are the gravitational force, right? Rather than 3 of our forces having components, now we just have 1. Okay? Yeah?
What if the incline's going that way?
It's exactly the same. You could just always shift down the incline to be positive.
Oh, so whenever, okay. So I can change.
Okay, so if we shifted our incline the other way, let me see. All right, it just looks like this. So now this is the positive direction, negative direction. Gravity still looks like that. Normal still looks like that. Right? It doesn't really make a difference which direction you choose to be positive and negative, as long as you're consistent with your forces, like positives minus negatives. Okay? But I always usually choose down to be the positive direction, down the incline. Okay? All right, since we have gravitational force pointing straight down, we have components of the gravitational force that we need to take into account. Okay, and we have a horizontal component we call force parallel. And the vertical component of our gravitational force also is called the normal force. And I'll show you why that's the case. Okay, so we have a force of gravity that pulls straight down. As I see my coordinate system, right, I'm going to line my coordinate system up here. The y component of my gravitational force is along that axis. My x component is along the x-axis. Do we see what's happening here? Okay, here's gravity. Here's the y component of my gravitational force and the x component of my gravitational force. Okay? The x component is called F parallel, the parallel force. It's not an 11. It's parallel. Okay? Why do you think it's called the parallel force? Parallel to the incline. Right? We should see that it's parallel to the incline. And it will always be that way regardless of how the incline is drawn. Okay? If the incline is drawn the other way, it will still be parallel. Right? The x component will still be parallel. So for parallel, we're always going to use sine. Right? Because it is opposite of that angle. Okay? I'll get to that here in a second. The vertical component of our gravitational force, believe it or not, is called the normal force. Because if I have a normal force, which I do because it's on a surface, those two are congruent. Okay? The normal force that we know about is congruent to the vertical component of our gravitational force all the time. Okay? So that's how we solve for normal force in inclined planes. We find the vertical component of that gravitational force. Okay? So to find Fg, what do? How do we find Fg no matter what? Okay, but if we're given a mass in our problem, how do we find? This is always mass times 9.8. So you always are going to have the ability to find Fg, and then you can use trigonometry to help you find the components of that. Okay, normal and parallel. Okay. Okay, the last thing I want to tell you, and I want to look at this diagram one more time. It will tell you the angle at which your incline is raised. It'll tell you this angle, right? We'll say it's on a 30-degree incline, okay? Based off geometry that I don't really need to know or care about, this angle always matches that angle, okay? Always. Okay? So the angle at which your box is being inclined will always fit into your gravity triangle, right there, okay? The one that touches your object. Okay, so it'll tell you the angle at which it's inclined. You can use that in trigonometry to help you find the parallel and the normal force. And then you solve it just like any other problem, right? Because now this is a horizontal force. Parallel is horizontal. Normal force is vertical. So in incline problems, once you break down Fg, you don't use that in your problem anymore, right? Because it's at an angle and we can't use that. Right, so you got to break Fg into the normal and the parallel, and then you use those components within your problem. Okay? All right, let's try one here. So I'm going to kind of write out the steps here that we're going to use to solve, and then our overall goal is going to be to find the acceleration of our box. I, for some reason, always draw my incline this way. It doesn't matter which way you draw it, but I always draw it that way. Again, it does not make a difference, but okay, it says we've got an incline that's been raised 30 degrees. Okay, that's that angle right there. So when I start drawing my forces, I have Fg and Fn, right? That's it. I don't have any applied force because I'm not pushing the box. I set it on the incline, and it slides. Yeah, we don't have to draw the axis if you don't want to, but we do need to break that gravity triangle down, okay, into its x and its y component. So the x component is always called parallel force because it goes parallel to our incline, right? And the vertical component is always called the normal force, okay, because these two are congruent to each other. Okay. Any questions with how our diagram gets drawn?
Are the two F's always parallel?
They're always congruent. They're always going to be equal to each other. Yeah.
Why didn't you draw the triangle connected to the other side?
Okay, so when we draw our gravity triangle, FG always needs to be the hypotenuse. I should have said that earlier. So you can't draw it to make your right angle like that. Okay, your right angle doesn't go here. Right angle always has to go here. So I draw the triangle this direction so that it matches my new coordinate system. Right? My coordinate system goes like that. So I want one of them to be vertical and one to be horizontal. Okay, so it's really important that when you draw that gravity triangle, the right angle has to go between normal and parallel. FG has to be your hypotenuse of that triangle. A lot of people will get into the habit of drawing the triangle like this. Right? That's no good. Okay? Hypotenuse has to be FG. Okay, does that answer your question? Okay. All right, so we've got everything drawn. That's all for FG. How do I find gravitational force?
10 times 9.8.
Good. And M times 9.8. 98 newtons, right? Once I find my FG, it's in newtons. So I know that's the hypotenuse of my triangle. Okay? Then what do I know my angle is? Right here. 30 degrees. It matches the angle on the incline. So 30 degrees fits right into here, and I can't quite fit it in there, so I'm just going to draw it. Okay, 30 degrees goes right there. So to find the parallel force, I would use sine or cosine? I use sine. And that is always the case. So this is one of those that you can memorize the rule here. To solve for parallel force, you're always going to use sine. Okay, so I take 98 times sine 30. And then for the normal force, I take 98 times cosine of 30. Okay. Last thing that sorry, is there any questions so far? Yeah.
Why is the angle...
Something like that. Okay. Last thing we want to do is find acceleration. Do you think we're looking for vertical or horizontal acceleration? Where does your horizontal axis, remember, runs along the incline now. So we want to find horizontal acceleration, which means when we set up our net force equation, what's our positive horizontal force? Yeah, it's our parallel, which we know is 49, right? Parallel is what's pulling it down the incline, okay? The horizontal component of our gravitational force is what's pulling it down the incline. Is anything opposing it? No friction, nothing like that. We didn't talk about friction. You weren't given a coefficient of friction, so there's nothing. Okay, so you can put a minus 0 if you want, but you don't have to. Okay, so I'd say 49 equals F net, which we know is mass times acceleration. And that means our acceleration is equal to 4.9 meters per second squared. Okay? So in this case, we didn't need our normal force. Right? We didn't plug it in anywhere. But where do you anticipate needing our normal force in future problems?
Friction.
Yeah, remember our equation for friction is coefficient times the normal. So normal will have to be applied in cases when we have friction. So you didn't have to necessarily solve for it on this one, but it's an okay habit to get into to just do both of them. Yeah?
So when we're finding Fn for the friction formula, you don't have to do like the positives minus the negatives.
Not for this because Fg is not necessarily equal to Fn, right? And so in here, you're just finding the normal force based on the component of that gravitational string. All right, let's go ahead and try this one. 33.3 degrees. That is our ESG. Good. This problem, 466, is Fg. They already took the mass times 9.8 for you. Since it's measured in newtons, okay, we know it's already Fg. So Fg is already equal to 466. Okay, they already took mass times 9.8 for you. The way you know that is with the unit. If it was mass, it would be kilograms. If it's Fg, it's in newtons. Okay? So let's see here. Our diagram looks something like this. Our diagram is again frictionless. And the angle that fits right here is 33.3 degrees. Fg is equal to 466. Okay? The overall goal of our problem, it says, how long will it take? So what's that mean we're solving for overall? How long will it take? That means we're looking for time, right? Overall. But we can't get to time until we have the acceleration of our object. So that's what we use our free body diagram and all of our forces for. And then once we solve for acceleration, what can we do to get time? We're going to have to use our kinematics equation to solve for time. Okay, so kinematics don't go away just because we're done with that chapter. And they don't go away. All right, so for parallel, we're taking hypotenuse times sine. Make sure your calculator's in degrees, not radians. 255.8. Normal force is 466 times cosine. 389.5. Okay, so now we know we need to get acceleration. How fast is it accelerating down the incline? What's the only force pulling it down the incline? F net equals parallel. That's our positive horizontal force. There's nothing opposing it, right? No negative horizontal forces. So parallel is 255.8. My mass, how do I solve for mass? Okay, that's an important step. So mass is not 466. Fg is 466. So I need to set 466 mass times 9.8 equals 466, and I get, perfect, 47.6 kilograms for our mass. Okay, does that step make sense? That's going to be a step that we haven't really done before, but I need to make sure that it's making sense to everyone why we did that. Okay, assuming it starts from rest, we can use our second kinematics equation. So final displacement is 8.45 meters. We assume it travels the whole distance of the incline. Okay? Initial displacement 0, initial velocity 0, 1/2 a, times t squared.
Oh wait, can we do this?
No, I was just waiting for you to get written down what you need to.
Oh.
I'm just drawing the diagram. I'm waiting for you to get written down. We'll do it together. I'm just giving you time to get the diagram down and anything else written down that you want. Okay, so first thing we have to do in all of our problems is find that gravity force. Find the gravitational force, which we know is what times what? Okay, so in this problem, our mass is 20 times 9.8. That's how we get our FG, 196. Okay, FG is 20 times 9.8. Okay, do we have our normal and our parallel force? Okay, parallel will take 196 times sine of 50. And for normal, do we need both of these?
Yes.
Yes, we will because we have friction this time. So we have to have both of them for sure. Okay, did we get around 150 and around 126?
Yes.
Okay, for those two. All right, parallel force, normal force, we got all that. You can solve for the frictional force totally by itself and then plug it in. It doesn't matter the order that you do things. So I'm going to go ahead and just set up my net force equation. Okay, and I'll say F net equals, what's my positive horizontal force? Okay, good. It is my parallel force. And then my opposing force is friction. Okay, and I knew there was friction because it gave us the coefficient. It didn't specifically say the frictional force is blah, 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 right? It gave us the coefficient. That should be like a little red flag that tells you, hey, I have friction I have to take care of, okay? So if I start putting in numbers, I could say parallels 150.1. Friction, I take the coefficient, so 0.4, times my normal force, which is 126. And my mass is 20, and I solve for A. Okay, that's it. Okay. If it makes more sense to you to just solve for frictional force by itself, like we did with these, right? Take coefficient times the normal, get a number, then plug it in, great. Or if it's just better for you to just do it all one time, great. It doesn't matter. Acceleration somewhere around 4.99, 4.98. Yeah. 4.985, so as much rounding as we can do here. Meters per second squared. Try this one on your own. I don't have them on this one. Okay,